Hi, this is Dot Cross and Nabla with our third video in our Calculus 3 series, and today we're going to be going over the cross product. So in our last video, we were talking about the dot product, a type of multiplication between two vectors that returns a scalar. But in this case, we're going over the cross product, which is another way to multiply vectors that returns a vector instead of a scalar. So before we even start off, let's try and give like a real world example or like even like a physics application of the cross product, right? So suppose you want to loosen a bolt with a wrench. As you apply force to the end of the wrench and the plane perpendicular to the bolt, the twisting power you generate depends on three variables: your force, your length r, and the angle at which the force is applied, right? So let's say, for example, I have a lever like this, and let's just call it like, I don't know, 1 meter. It's probably not fully accurate, but you get the idea. And we have a force that is like in this direction, F. This is the theta. Let's just say theta is about like 60 degrees. If I want to maximize my torque or my rotation to unscrew the bolt, I want everything to be perfectly perpendicular, because it's kind of like if you're opening a door right by, if you're opening a door right by its hinges, you're not going to generate any torque, right? It'd be better to open the door right here. That's why the door handle's right at the end, right? Because it's a greater R. And also, you're going to be pushing straight across. You're going to be going like this. You're not going to be coming in from the side like this. You're not going to generate as much of a rotation to open the door, right? And it's the same idea with the wrench, right? You would want the force to be completely perpendicular. So you want it to be a whole 90 degrees over instead of it being 45 degrees or 60 degrees, right? And in physics, you have the definition of your torque as being RF sine theta. But in fact, what we're actually doing is the cross product. We're crossing these two vectors. And you normally don't think, you can think of force as a vector in physics because force just equals your mass times your acceleration. And as we know from 11.1, 11.2, acceleration is a vector that we've been going over. But your radius is also a vector. It's pointing out in whatever the direction of like the tool is, right? Or this, right? And this dot right here, let's just put it in red. This dot right here represents our pivot point at which we're rotating or unbolting the screw, right? And yeah. Then we get to the actual definition of what the cross product is. So you're given two non-zero vectors, u and v, in R cubed. What this just means is just like you're in 3D space. So this is just meaning 3D space. And when we're given these two non-zero vectors, u and v, in R cubed in 3D space, the cross product uv is a vector. So this is a vector quantity, not a scalar quantity. So this means it has a direction and magnitude, with the magnitude of u times the magnitude of v times sine theta, right? Where theta varies from 0 to pi is the angle between u and v. The direction of u and v is given by the right-hand rule. When you put the vectors tail to tail and let the fingers of your right hand curl from u to v, the direction of u to v is the direction of your thumb orthogonal to u and v. So we can go right here and we can see this, right? So if I were to use the right-hand rule, I would say I would put my index finger in this direction, and then I would have my thumb come out, not my thumb, my middle finger come out in this direction. And then you have your two fingers like this. If you're on a tablet, it's easier to visualize. You have it like this, you're gonna curl up. And as a result, you're gonna get this resultant vector u cross v that actually comes up. However, if you do v cross u, your v is gonna be your index finger, your u is gonna be your middle finger, and then when you do the right-hand rule, your curl is gonna be clockwise. It's actually gonna be in the negative direction, right? So there's a couple of things to keep in mind. We can actually write that down real quick. So a counterclockwise curl equals positive cross product, and a clockwise curl equals a negative cross product. And if you think about it, it makes a little bit of sense because on our unit circle, the way we rotate, we are rotating positive with radians when you go counterclockwise, right? We go from 0 to pi over 2, from pi over 2 to pi, and so on and so forth, right? So that's like a relationship that you can think about as you go along with this, right? And yeah. And then our last thing is when u cross v equals 0, the bold again refers to the arrows of these vectors, right? So we'll just put that in there just for clarity. When u cross v equals 0, the 0 vector, the direction of u cross v is undefined. In part because if we have our 0 vector, this is what we defined in our earlier sections, this just refers to, and if we were to put this on the xyz plane, our 0 vector is just right here. It has no direction, it has no magnitude either, because the magnitude of it would be 0, right? According to our definition of magnitude, which we went over again. We can just write it out just one more time to really hammer in the concept, right? Take the magnitude of that, it's just gonna be 0, so that's another property of the 0 vector. And for example 1, we want to sketch the vectors u equals 1, 2, 0, and v equals -1, 2, 0. Which way does u cross v point, and which way does v cross u point? So this is kind of something we were getting at a little bit earlier with the right-hand rule, and you can apply that in this example, right? So we can draw out the sketch real quick. One of the things in Calculus 3 you have to be very good at is knowing how to sketch properly. And knowing how to sketch properly will save you so much time in visualizing kind of difficult, more abstract concepts. And if you don't know how to sketch, it's not the end of the world, but it just makes your life so much easier, right? And in this case, I'm gonna use different colors to represent what u cross v is and v cross u is, right? So I know that u and v don't have a z component, so it's gonna be easier to sketch this. So we go 1 in the x direction, and then 2 in the z direction. So this is gonna be my u vector. And then I'm gonna go 1 here, but I'm gonna go 2 in this direction, and then I get my v vector, right? And then in this case, you can just apply your right-hand rule. So if I come on the side of the u, I see that it's gonna be u, my u goes in this direction, my index finger goes in the direction of u, and my v goes in the direction of my middle finger, or my middle finger goes in the direction of v, excuse me. And then you curl, and then the resultant vector you should get should point upward, and I'll label that in green in this case, where this becomes u cross v, right? However, if we were to do v cross u, you would have your index finger as your v, and then your u as your middle finger. Your middle finger is going to be the u, and then you rotate, you do the right-hand rule. Your curl, you're going in the negative direction, so you're actually going to be going in the negative z direction. So that's going to be what v cross u is. However, given our definition of the cross product, where we said that it would be equal to the magnitude of u, the magnitude of v, sine theta, the magnitudes are the same. It's just the direction that's different, and the direction is only going to be determined by the angle of the vectors, or the way you're crossing them, right? So in this case, it does matter what order you go in. In the dot product section, when we talked about it, if we dotted these two vectors, in fact, we could just do that right now. It would be u dotted with the v. It doesn't matter what order you go in. It's because you're just multiplying, right? If I were to write it like -1, 1, like this, you still get the same result. You still get the same scalar quantity, but in this case, you don't. So it actually matters what order you're crossing these vectors, because you could get, in the u cross v case, you could get it pointing upward as your cross product, or pointing downward if you were to do v cross u, right? Now we're going to an evaluation of the cross product. And this is where matrices come in. This is a little bit of linear algebra. It's not too crazy. The method that I would recommend is, if you're getting stuck on this, what I always do is, if I'm doing the I, j hat, and k hat components, because that's what you would have to do to solve for this, is you cover up one of these. You cover up the I hat, for example, and you're gonna do this times this, this times this. You subtract the two, you get I hat, right? And then you would do the same thing for j hat, but in this case you have to remember there's a negative. And the negative is just there because it's a property of the cross product where it's gonna have to go into the negative j hat direction. It's kind of out of the scope of this video per se, but it's just like important that you have the general formula memorized. I guess not memorized, but like understand how it works. And then you would just ignore the j hat in this case. You go straight across, you subtract, you like that. And then you do the same thing for the k hat. You ignore this and you just do as such. And in this case, we can actually apply this, because now these are like simple 2x2 matrices. And we can either use this definition or use this definition. Probably better to be using this one because it pops up more often than not in these examples and in problems related to the cross product. So we can just work through it real quick. So let's just say we have this, right? So we can just ignore this for now. We're gonna have u2 v3 minus u3 v2 I hat. Perfect. Then we can ignore this right here. Let me do minus u1 v3 minus u3 v1 j hat plus, let's get rid of this now because we need to use this for the k hat component. Scribble over this plus u1 v2 minus u2 v1 k hat. And these just represent, again, our unit vectors in each of the three Cartesian planes x, y, and z, right? And that's how you would solve for the cross product of the vectors, right? Of two separate vectors. In example 2, we actually have an example of us going through how to solve for the cross product between two vectors. And in this case, we still have to follow the order of operations. And if you'd like to try this example on your own, given what you know, feel free to pause the video. One thing I will say, though, is we still have to apply PEMDAS. So it's going to be the order of operations. It's going to be B cross C that we do first. So yeah, so we're going to try that. So I, j, and k. -2, -1, 0, -2, -3, -1. Okay, I'm gonna put my thumb over the I hat real quick, and then I'm gonna get -1, -1 times -1, minus 0 times -3. So this goes away, I hat. Then I'm going to have minus, cover up the j hat component. It's going to be -2 times -1 minus 0. So that goes away. J hat, so it's going to be plus plus. It's still going to be minus. And minus, I'm going to cover up the k hat now. It's going to be, it should be plus. It's going to be -2 times -3 minus -1 times -2. You're gonna get a lot of negatives, so you gotta clean this up, make it easier for yourself. K hat. This is gonna be -2 minus -3, so it's gonna be plus plus. 6 minus 2 is 4. So now we have our final result. So it's gonna be plus plus. It's gonna be 1 I hat minus 2 j hat, because we still have the negative out here. And then we're gonna have plus 4k, because it's going to be 6 minus 2 here. So then this is going to be what B cross C is. And if I were to do C cross B, all my values for I, J, and K would be flipped, actually. So it would be -1 I hat plus 2 J hat minus 4 K hat, because of what we showed earlier in example 1, right? But now we can do the actual A cross B now, A cross B cross C. So let's do that real quick. So A is going to be first. 1, -2, 4. And this is the same process, so it's just going to be place your thumb over the I hat. It's going to be 3 times 4 minus -2 times -2 times 1 I hat. It's going to be 12 minus 12 plus 2, so it's going to be 14 I hat. Then we're going to cover up the J hat, so it's going to be 3 times, it's going to be 3 times 4 again. Minus that, it's minus 1 times 1 J hat. So that's going to be negative times 12 minus 1. So it's going to be minus 11 J hat. And then we're going to cover up the K hat now. So now it's going to be plus 3 times -2 minus 3 times 1. 3 times 1, which will get us -6 minus 3, which is -9 K hat. So it's going to be -9 K hat like that. And then our resultant vector is going to be 14 I hat minus 11 J hat minus 9 K hat as our resultant vector. And now we have another theorem that we're going to go over with respect to the geometry of the cross product. So like we mentioned in 11.1, 11.2, when we were working with how to solve for the definition of like the cross product, or solving for like tip to tail, adding up vectors, right, tip to tail. We can do that again in this example. Let's just say we have some arbitrary vector, just label them in different colors now. Say we have some arbitrary vector u in this direction, and some arbitrary vector v in this direction, right? If I were to copy, paste, and just like transpose it on this, we can make a parallelogram. And the parallelogram is going to be nice because as a familiar formula we can apply, that being that we know the area of a parallelogram, I know I spelled that wrong, but bear with me, is going to be base times height, right? Let me just label these again so we know that these are the same. And we know that these are going to be parallel because of geometry, and this has some base angle theta, right? What we can do now is, if we want to solve for the area of this given these two vectors, what we can do is solve for our height, right? Our height h, and we can replace it in the vector, right? And in this case, what we can do is say that we want to solve for our h, we know theta and u, we can use right triangle trig. We can say that the sine of theta equals my opposite over my my hypotenuse, and in this case my hypotenuse is the magnitude of this vector, right? So then my h, we can call h actually in green, how about that? Makes our lives easier. We can say that h sine theta, no, actually not, sorry, not h sine theta, u, magnitude of u sine theta equals h. And our base, which we haven't gotten to yet, is going to be the magnitude of v, right? So then we can say that the magnitude of v, magnitude of v times the magnitude of u times sine theta, this corresponds to this part, and this corresponds to this part. And what do we know about this definition? We just flip the order of this. It doesn't matter if we flip the order of this, because the magnitude times the magnitude of something else is going to stay the same regardless, right? What we can say then is that this equals the magnitude of u cross v. So in essence, we just solved for the area of a parallelogram using two separate vectors, right? And in fact, we can generalize this to any type of parallelogram. So it can be a rectangle, it can be a square, right? It can be any form as long as it can be considered a parallelogram by geometric definitions, right? So it has two sets of parallel sides, like in this one. Yeah, and we can also relate this to triangles too, because the area of a triangle, base times side over 2, just sub this entire formula. Let me get that little dot, into the equation, just divided by 2. Perfect. And now that we did that, we can go on to example number 4, in which we're going to cover how to solve for the area of a triangle with the vertices like this, right? And in this case, we want to still have two separate vectors, right? But the nice thing with this example, and if you want to try this example, feel free to pause the video now, is that we have one of our points at the origin, right? So it's going to be 0, 0, 0. So the nice thing about that actually is that when we're doing like the solving for like the vector like we did in 11.1, 11.2, we don't actually have to do anything. We can just do this and this. But I still want you guys to get into the habit of forcing yourselves to be like, okay, it's q like this, cross. You have to still do the annoying subtraction, even though it's all zeros in this case. Cross. Oop. And we can still get to the cross product from here. And we can do I hat, j hat, and k hat. 2, 3, 4, 3, 2, 0. And the nice thing about this is that we're taking the magnitude of it, so it doesn't matter what order you choose. You could have chose QO cross PO or PO cross QO, or you could have done OP cross PQ, right? You could choose or OP and QP, right? You could have chosen any form, and you still would have gotten the same answer. Just taking the magnitude, right? So in this case, we're just going to perform our cross product rules, right? So I'm just going to do it out real quick. 3 times 0 minus 2 times 4. So 3 times 0 times 2 minus 4, right? Yeah. I hat minus 2 times 0 minus 3 times 4 j hat plus 4. Well, we don't know what's 4 yet, but just 2 times 2 minus 3 times 3. And then we can just do all the addition from here. So it's going to be 0 minus 8, negative 0 minus 12, 4 minus 9. So then we can get negative 8, 12, and negative 5. And then we can just apply our definition of the area of a triangle given two separate vectors. Oops, I want to copy the whole thing in. It's not going to work, but we can just now say that, take the magnitude of this, which we know is just going to be 8 squared plus 12 squared plus 5 squared. So this is going to become 64 plus 144 plus 25. So it's going to be 208 plus 25, so it's going to be root 233. But we have to divide by 2 since it's the triangle and not a parallelogram. And that would be what your answer is, right? Now we have probably the hardest example in this entire video, trying to solve for the area volume of a parallelogram prism or a parallel pipette determined by the sides A, B, and C. This is a really difficult problem. If you want to try this on your own, feel free to pause as we will work through this. This took me a little bit of time to wrap my head around, so if it looks confusing for you looking at this for the first time, I understand completely. So when looking at this, I always like to go back and refer to my handy idea that volume equals base times height, right? And we're already given the base. We see it's B and C, and we know that we can just say that the base is just going to be the cross product of B and C, the magnitude of the cross product, right? As we derived up here. Or we can just say it's going to be UV sine theta, or B, magnitude of B, magnitude of C sine theta. But we can just leave it like that, right? It doesn't matter that much. As for the height's going to be a tricky relationship to figure out. But what we can notice is that our H, as poorly as it's rendered on this screen right here, this is going to be considered alpha. We know that there's going to be a relationship between H, A, and alpha, where it's going to be H equals, actually no, let's not do H. Let's just say we know, that, oh shit, this is not, yeah. We know that this is a right triangle. We know that this is our hypotenuse, this is our adjacent side. So then we can say that the cosine of alpha equals the H adjacent over hypotenuse, right? So we can say that, well, this is going to be the magnitude, right? The magnitude of A cosine of alpha equals H. And then we can just solve for our answer right here. You can plug it into here, times magnitude of A cosine of alpha. And the nice thing about this actually is what we can do is we can rewrite it as a separate type of equation, where we can say that our height in essence is also going to be equal to the cross product of B and C times the dot product, dotting it with A, right? All over the magnitude of A cross B. Oh, sorry, not magnitude of A cross B. Sorry, the magnitude of B cross C. And in essence, this still works out like this, because what we're getting at is that all this is giving us is A right here. A is going to be orthogonal to B and C in this case, right? If we apply our right hand rule, it's going to go in the direction of A, and that's how you would solve for that. And then finally, we're going to go over some of the properties of the cross product. So we have the anti-commutative property. This is the example we did earlier where we're doing example 1. In fact, we're talking about how if you cross these two vectors in the opposite direction, if you cross them one before the other, you get it in the complete negative direction, right? So that still works. The associative property, this works because you can pull out the scalar quantities from a vector. You can still multiply them after, so that works completely fine. You have the distributive property, where this kind of works like you can just multiply this out to these two, and you'll still get the same result. And then again, another form of the distributive property, it works both ways. Just multiply that out. And then we have to determine whether or not each of these expressions make sense or not, and if it makes sense, explain why it would be a scalar or a vector given those properties, right? So feel free to pause the video and try these examples on your own. All right. So in this case, we're going to do v cross w. I'm not even going to like give them like fake vectors or whatever. We're just going to go over, right? So if we cross two vectors, we get a vector. So then I have a vector dotted with a vector now. So a vector dotted with a vector just gives me a scalar. If I cross two vectors, I get a vector. And then if I have a vector plus a vector, I get a vector. So that's also a vector. This is a scalar. If I dot two vectors, I get a scalar. Scalar cross vector doesn't work because you can only dot or cross two vectors. You can't dot a scalar with a vector because it doesn't have a direction that can be defined, right? D, we're going to cross these two vectors, we get a vector. And then we add another vector, so it's going to be vector plus vector, gets us a vector. When you add two vectors, you get a vector. When you add two vectors, you get a vector. So then a vector cross a vector, definition of the cross product, we get a vector. And then for example, F, we do A dot B, which is going to get us, because there's going to be multiplication before addition, it's going to be a scalar plus a vector. You can't add them. They're different things, right? Because a scalar only gives you a value, it's like 3 pi e. A vector is giving you a direction of sorts. So you can't add those two together, so this also doesn't work. And finally, going to our real-world example of torque, like we mentioned at the beginning of the video, we can say that the torque or the twisting effect produced by the force about a pivot point O is given by your radius from the pivot to the point of the force crossed with the force, and if you take the magnitude of that, you get magnitude of r, magnitude of f sine theta, right? And remember, sine theta is a function that gets its max height at pi over 2, right? And it can only go from 0 to pi over 2. So right here is where pi over 2 is. This is where pi is. This is where 0 is. And it's from theta to, I guess like the value of sine theta, right? And we have an example 5 right here. So this example, we want to see which produces more torque and what is the direction of each respective torque, right? So we can just apply the rules of torque here. So we can just say magnitude of r, magnitude of f, sine theta. You just copy that over to save some time. So what's the magnitude of r in this case? It's going to be 0.15 times 20 times sine of 60. So this is going to become root 3 over 2. This is going to become 3, so it's going to be 3 root 3 over 2. And in this case, it's going to be 0.25 times 20 sine of 135. This becomes root 2 over 2. This becomes 5 root 2 over 2. And then if you were to compare these two torques, the magnitudes of the torques, we can say that we know that, just plug it into your calculator, actually, we can do 2.6 Newton time meters, because this is going to be in meters. The radius of your object that you're rotating, the m, This is going to be n. This has no it has no unit attached to it. Same thing with this, just going to be meters, newtons, no unit attached to it, right? And this is going to be 3.54 Newton meters. So this one has a greater torque than this one. So example 2 is a greater torque than example 1. And if you were to solve for the direction of it, you would just do the right-hand rule. So it's going to be R cross F. So R is the direction of the red. So you're going to use your pointer finger for that. And then your F is going to be the direction of the force applied. It's going to be tip to tail. And then you cross it. It's going to point out of the page. It's going to point up, right? And usually what we do in physics and calculus is that we say if something is out of the page, we usually put like dots around it, right? If something's into the page, we usually put like X's, right? And think about it like that, it's like an arrow's coming out at you, right? Versus the X, it's like it's going into the page. Same idea, we're gonna do this again. So our red is gonna be the point, our radius, it's gonna be R cross F. It's gonna be like pointer finger is gonna be in the direction of P. And then the force is gonna be your middle finger. You rotate, it's gonna point up again. So in both cases, they're gonna be pointing out of the page. And that is it. Thank you so much for watching, and I hope you all have a fantastic day.